Right, welcome to the Modular Universe's video extra. For any rule with integer inputs, the slope's got to be rational. Well, that's exactly what we're doing when we're looking at our plot. We're going an integer number across and an integer number up. You know, we're on a plot. It's a whole number of trees across and a whole number of trees up. And so if we think back to our donut sequence, we might suspect that at some stage we're going to start repeating. And as we just saw, if we looked at plot n, and we applied our rule n times, well then we automatically get back to the beginning. So that says on plot n, we'll have at most n points on our line. Kind of crazy, huh? So suppose we take the rule that goes across 1 unit and up m units. Well, now we have an integer slope. We've gone across 1 unit and up m units. Well, on plot n, suppose we apply this rule n times. Well, it's going to go across 1 unit, 2 unit, 3 units. It's going to go across n units. So we're going to have to end up on this far side. Well, if I've applied it n times, and each time goes up m, how far up am I going to go up in total? I'm going to go up m times n in total. And m times n is the same as n times m, which means that I just end up in that top right corner. And that top right corner is the same as the bottom corner. So after applying our rule, 1m, n times on plot n, we get back to that bottom corner. Here's the interesting thing though. If I hit the top edge earlier, then that's the same as the bottom. And so whatever I did in that little sequence there has got to happen again in this next little sequence, and I've got to hit the top edge. And so this chunk here, this length here, has got to be the same as this length. It's got to be the same as the next one, and so on and so forth. And eventually I've got to get to that far side, so that getting all the way across has to be made up by a sequence of chunks that are the same length. In other words, however far I've gone across, the first time I hit the top row, that number of columns has to divide the total number of columns. So the width of that first sequence that gets to the top edge must divide the whole width of the plot. So for instance, if I was on plot 4, the first time I hit that top row could either be the first column, the second column, or the fourth column. It couldn't be the third column if I'm using rule 1m. Conversely, if I was on plot 5, then the first time I hit the top row would either be the first column, or I'd have to go all the way through to the end, to the last column, because there are no other divisors of 5. 5 only has 1 and 5 as its two divisors. It's being prime. Now here's the magic catch. I can't actually hit the same row twice before hitting the top. Because if I did, I could sort of unapply the rule from the second one, and however many times I unapply the rule to go from this first one back to the beginning, that same number is going to take me back to the bottom row over here, which is the same as the top row. Make sense? So when we're looking at a plot that is modular prime, not only do we hit each column once, unless we hit the top row right at the beginning, we're actually going to hit each row once. So if we're thinking about plot 5, applying the rule once gets me m, applying the rule twice gets me 2m. Well, I have to think of the remainder of 2m after I divide by 5. Applying the rule 3 times gives me 3m, or the remainder after dividing by 5. Applying the rule 4 times gives me 4m, or the remainder after dividing by 5. And so m, 2m, 3m, and 4m have to land on different rows, i.e. leave different remainders, 1, 2, 3, or 4, after dividing by 5. Now it doesn't have to happen in that order. For instance, this. Alright, if this all feels like it's kind of on that cusp of making sense, but doesn't quite, or if it's a little bit of a fog out there, but you're almost seeing through it, don't worry. That's what it's like when you're on the frontiers of the mathematical wilderness. The good news is that you're in safe hands here. It's almost like we've got an entire support crew behind us, in the form of the Rule the Trees handout. In fact, it might be worth revisiting that just to cement your understanding. But it is kind of fun to think of what it must have been like to be one of the first explorers to explore this land. Kind of like heading out across the Great Plains in search of a new country. Now the mathematicians who've gone before us here, they developed some useful notation that sort of encapsulates what's happening here. We say that A is congruent to B mod n, written like this, whenever A and B leave the same remainder after dividing by n. So for example, 3 and 8 are congruent modulo 5. Written 3 is congruent to 8 mod 5, because 3 and 8 both leave a remainder of 3 after I divide by 5. Now I have to confess, mathematicians being mathematicians sometimes get a little bit lazy, and if it's understood what we're looking modulo, the modulus, then they sometimes drop that mod 5 part from the expression. So this means for any prime number, let's take 13 for example, so think plot 13, and any number less than that, let's take 4 for example, there must be some multiple of 4 which leaves a remainder of 1 after dividing by 13. Well, let's just check it out. What have we got? We got 4, 8, 12, 16, 20. Well, 20 is actually the same as 7. 24, 28, and so on and so forth. And 40 gives us 1. And 40 gives us 1. Note, I'm being a little lazy here. I'm dropping our modulus. So in this instance, 10 times 4 is congruent to 1 mod 13. In other words, 10 is sort of an inverse of 4. 10 is sort of like a quarter mod 13. And we can actually make really good sense of that. So when we're working modulo a prime, all whole numbers are either congruent to 0, meaning they're divisible by that prime, or they have an inverse modulo that prime, which is kind of crazy. It gives rise to all sorts of interesting ideas, but unfortunately, that's for another day. Of course, this doesn't work if our modulus isn't prime. So for instance, if we were looking modulo 6, we could have 2, 4, 0, 2, 4, 0, 2, 4, and we never hit 3 or 1. There's no multiple of 2 mod 6 that ends up with 1. Sort of the same as looking at the rule 1, 2 on our plot 6. We never hit that first row. We saw that earlier on. Alright, before we go though, I want to just give you one concrete application to the real world. Suppose we were in a world where we had $5 notes and $2 notes, and we wanted to trade exactly $1. Well, I know that I can, because 2 has an inverse mod 5, namely 3. 2 times 3 is 1 mod 5. Well, what does that mean? That means 2 times 3 minus 5 leaves 1. I have $3 $2, and I give you $3 $2, and you give me $1 $5. I've just effectively given you $1. Alright, perhaps even more amazingly, if we were in a world that had only $19 notes and $17 notes, you and I could still trade exactly $1. Seems unreasonable, right? The difference is 2. How could we possibly do it? Well, you have a little play around and see if you can figure it out. Think about finding an inverse of 17 modulo 19. Or an inverse of 19 modulo 17. See if it makes a difference. Alright,